Hello, and welcome to your mini lecture covering redox reactions from our Chemistry 1412 class with Dr. Elizabeth Bell. Today we are talking about oxidation and reduction reactions, which are called redox reactions for short. Redox reactions occur all of the time, all around you, and also inside you. When you breathe, your body takes in oxygen and lets out carbon dioxide. The oxygen was reduced in this exchange. Plants take in carbon dioxide to make oxygen via photosynthesis. The oxygen is oxidized in that exchange. Anytime organic material is combusted, redox reactions are occurring as well. When an atom loses electrons, it is oxidation. When an atom gains electrons, it is reduction. The way to remember it is oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. Here we see a reaction between neutral zinc and the silver 1 plus ion. The zinc gives silver an electron. The silver gains that electron. Zinc is oxidized and the silver ion is reduced. Notice that we need 2 silvers to react with 1 zinc because zinc is losing 2 electrons, 1 each to the 2 silver ions. When you break the reaction up into oxidation and reduction reactions, these are called half reactions. Here we see a copper wire with a silver nitrate solution being poured over it. The neutral copper reacts with the silver plus ion to create the blue copper 2 plus ion and this neutral silver. The gray-white crystals you see forming are neutral silver atoms. The copper goes from a charge of 0 up to 2 plus. This is oxidation. Silver goes from a charge of 1 plus down to 0. This is reduction. Redox reactions are what power batteries. Here we see artifacts from what is called a Baghdad battery. It is a clay pot with a copper tube and lemon juice inside. And an iron rod is suspended into lemon juice and held in place with pitch tar. There is a redox reaction which occurs between the copper and the iron. The reaction spontaneously produces an electric current. This setup is called a galvanic cell. The ability to push an electric current through a circuit is called voltage. A volt is a joule per coulomb, and a coulomb is an ampere times a second. There is a constant called Faraday's constant, which will allow you to convert between moles of electrons and coulombs. Here is another setup of a galvanic cell. There are 2 electrodes, one of zinc and the other of copper. There is a salt bridge, which in this picture is a porous disc that allows the spectator ions to flow freely. The 2 electrodes are connected via a conducting wire. This wire carries the electrons that are being gained and lost in the redox reaction. The circle with the yellow light is a voltmeter. Volts will be read when the circuit is complete, as is shown in the picture. The circuit will be broken and no voltage will be read if, number 1, an electrode is removed from its liquid. Number 2, there is no salt bridge. Or number 3, there are no spectator ions to keep the solution's charge balanced. The zinc goes from being neutral to having a 2 plus charge. This is oxidation. Oxidation occurs at the anode. The blue solution has copper 2 plus ions. A voltmeter is used to measure voltage. Here we see a galvanic cell with one electrode made from copper in a copper 2 plus solution, and the other electrode made from zinc in a zinc 2 plus solution. The cell potential for this reaction is 1.10 volts. You can trace the circuit, which the electrons travel, from the zinc electrode through the black cable into the voltmeter, through the red cable into the copper electrode, into the copper 2 plus solution, through the salt bridge, into the zinc solution, and then back to the zinc electrode. If any of these connections are broken, then the circuit will open and the voltmeter will read 0 volts. There is another way to write out a redox reaction. It is by using cell notation. In cell notation, the anode reaction is listed first, then the salt bridge symbol with the 2 up and down lines represents the salt bridge, then the cathode reaction is listed last. If the atom or compound which is being oxidized at the anode changes physical state during the oxidation, then you separate them with a single up and down line. If they are in the same phase, you separate them with a comma. It is useful to be able to go from one type of notation to another. The amount of voltage that a cell can produce is called its cell potential. The cell potential is the ability of a cell to force electrons through a circuit. You can calculate each redox reaction's cell potential by using their reduction potentials. We will go over that in the next lecture. The energy of a cell can be used to do work. To calculate this energy, also known as the Gibbs free energy, we use the equation W equals NFE, where N is the number of moles of electrons being transferred in the redox reaction, F is Faraday's constant, and E is the cell potential. The amount of work is called the electromotive force of a cell. If we put the small exponent of an O on the values of Gibbs free energy and cell potential, we are stating at which temperature and pressure the reaction is being conducted. The little 0 or O implies standard conditions, or 1 bar of pressure and 298 Kelvin. It also implies a molarity of 1 molar. This has been your redox mini lecture from our Chemistry 1412 course with Dr. Elizabeth Bell. Please go to Sapling now and do the associated assignments. If you need help, please do not hesitate to contact me. I am happy to help. Which gain 2 electrons to become neutral copper. The copper goes from having a 2 plus charge to being neutral. The copper gained 2 electrons. This is reduction. Reduction occurs at the cathode. The way to remember which reaction takes place at which electrode is red cat, an ox.